On page 2 of notes today, we're going to look at a couple of different types of applications for distributive property and combining like terms. First, combining like terms, we can deal with perimeter problems. I like to think of two possible ways to do perimeter problems like this. First thing that you want to remember, keep in mind, is that when we're talking about perimeter, we're talking about adding up the side length of each side of a figure. So we can do this by simply writing this problem out horizontally, saying that this is x plus this side 2x plus 7 plus this side, which is another x, plus the top part, which is another 2x plus 7. Now it's one big long combining like terms problem. I have an x, I have a plus 2x, I have a plus x, plus 2x. Those like terms combine to give me 1, 2, 3, 4, 5, 6x. And then I can also combine my plus 7 and my plus 7 to give me plus 14. And I'm done. That's my combining like terms with a perimeter problem. Number 11, I could do the same thing, but now I'm going to have a lot of writing to do going across because I have quite a few terms. So one way I like to look at this is I'll go through and I'll start picking out my like terms. They're all listed here, just as I have seen them here. Since I'm adding everything, all of these first terms really have a plus sign in front of them. You can draw that in if you want, or you can elect to not put those in there. Either way is perfectly acceptable. I always find my largest exponent term first. In this case, that's x squared. Mark your paper so that you know you've used it. You have one x squared, another x squared, another x squared. All three of those are x squared terms. X squared plus x squared plus x squared is 3x squared. And then move on to your next term. That's, in this case, x. And again, I'm going to mark it, but I'm going to mark it different. I'm not going to put one underline under it, because it would say it's like terms with my x squared. So maybe I'll put 2 underlines under this one, and 2 underlines under this. It's also an x. 2 underlines under here. That's also an x. So now I have 4x, 4x, and 12x. When I add those together, I get 20x. So I have 3x squared plus 20x. Last, I have my constant terms. Again, maybe I'll use a squiggle, something that's a little different to mark my constant terms. Now I know that I've used them all. I have a negative 60 and a negative 60. If I want to use my calculator alongside, I can do that. I type in negative 60 plus negative 60 plus negative 12 plus negative 12. So if I type all of that in my calculator, so 60 negative plus negative 60 plus 12 negative plus another negative 12, I get a negative 144, which makes this minus 144. And there's my final answer. So two possible ways to do perimeter problems. The last part of today is talking about area model with the distributive property. So really what we're saying here is I have two possible ways to find this. What I want you to recall is that the area of a rectangle is equal to length times width, or base times height. So I could do this in two ways. I could find the area of just this piece. If I found the area of just that piece, it's 5 times 11, or 55. That's the area of this piece. I could do the same thing finding the area of the piece in the middle here. Because it's a rectangle, I know that this is 11 here, and that this is 11 times x, or 11x, which would make the area of the whole rectangle 11x plus 55. Now, a second way I could have done this we know, again, that this length here is 11. But I could write one expression to represent this length here. I know it's this piece here, which is x, and this piece here, which is 5. So I could call it x plus 5. If I draw this out, or write this as an expression, I'd say that the area is the length, which is 11, times the whole width, which I would have to put in parentheses and say is x plus 5. Now if you look, if I were to use the distributive property here, 11 times x is 11x. 11 times 5 is 55. So it's just two different ways of solving and finding the area if I'm given a rectangular problem this way. Okay. Let's do that again here. The side length here is 2x plus 4, because that goes from here all the way down to here. So I could state that the area is this width, 9, times the whole length, 2x plus 4. Then, if I were to use the distributive property, 9 times 2x is 18x, and 9 times 4 is plus 36. Well, that's what I have here. This piece here would be 36, because it's 9 times 4. And the top part would be 9 times 2x, which is 18x. 18x plus 36, or 9 times 2x plus 4.